The million-kilometer question. In the past, diesel engines could easily exceed 800,000 or even 1 million kilometers. Taxi drivers trusted them. In fact, mechanics didn't even like those engines much because they rarely broke down. They became famous for their durability. However, today many modern engines start developing problems after 200,000 kilometers. Timing chain issues, turbo failures, carbon buildup, oil consumption. So what changed? Did engineering get worse, or did priorities shift? Old engines were built to endure. Older engines were extremely overbuilt compared to modern ones. Engine blocks were thicker. Internal components were heavier. Piston rings were stronger. Tolerances were more forgiving. They were not optimized for weight reduction or maximum efficiency. It was clear they were built for longevity. Power output per liter was lower. That meant less stress on each individual component. Operating temperatures were lower. Turbo pressures were more limited, or in many cases, there was no turbo at all. There were fewer sensors, fewer electronic modules, and not many systems that could fail. Fuel was cheaper, and emission standards were more flexible. Engineers had greater freedom. Reliability came before efficiency. Engines were designed with a large safety margin. Emission regulations changed everything. The biggest turning point was emission regulations. Governments around the world demanded lower carbon dioxide emissions and cleaner exhaust gases. To meet these new global standards, manufacturers had to completely redesign engines and adapt to new laws. Modern engines operate with higher compression ratios, leaner air-fuel mixtures, and higher combustion temperatures. Systems such as EGR, DPF, SCR, and complex catalytic systems were introduced. These systems protect the environment, but at the same time, they increase thermal stress and mechanical complexity. As complexity increases, the number of potential failure points increases as well. Higher temperatures mean more long-term wear. Modern engines now operate under tighter tolerances and higher pressures than ever before. Downsizing, small engine, big load. Another major change was downsizing. Today, a 1.0 or 1.2-liter engine can deliver the same performance as a 2.0-liter engine from 20 years ago. That is impressive, but it comes at a cost. High turbo pressure increases cylinder pressure. Smaller engines are forced to work harder to produce the same power. Pistons move faster. Bearings carry more load. Cooling systems operate closer to their limits. Older engines had a larger mechanical safety margin. Modern engines operate on a much thinner line between maximum efficiency and maximum stress. They are more optimized but less forgiving. Direct injection and carbon buildup. Direct injection improved fuel efficiency and power output. Fuel is now injected directly into the combustion chamber instead of the intake port. This provides better combustion control and lower emissions. However, this system removed a natural cleaning mechanism. In older port injection engines, fuel washed over the intake valves and kept them clean. In direct injection engines, intake valves no longer receive that fuel wash. Over time, carbon deposits build up on the intake valves. This reduces airflow, negatively affects performance, and can cause misfires. It is not an immediate engine failure, but it is a long-term durability issue that older engines did not have. Driving habits have also changed. Not only engines have changed, driving habits have changed too. Today, there are more short trips, heavier traffic, and more frequent start-stop cycles. Engines are often shut down before reaching optimal operating temperature. When the engine does not fully warm up, oil does not reach ideal viscosity. In other words, instead of flowing like water, it behaves more like thick honey. Moisture and fuel dilution inside the oil do not evaporate properly. Wear increases. The turbo may be shut down before it fully warms up. Modern engines demand proper maintenance. Correct oil specifications, timely oil changes, and quality fuel are more critical than ever. Neglect shows its consequences much faster compared to older engines. Not weakness, but engineering balance. Modern engines are not poorly designed. On the contrary, they are highly advanced technologically. They are more powerful, more efficient, and significantly cleaner. However, they are designed for balance. Performance, efficiency, emissions, and cost must all be met simultaneously. Manufacturers typically design engines to run reliably for 200,000 to 250,000 kilometers with proper maintenance. Older engines were built to withstand abuse. Modern engines are built to meet regulatory and efficiency targets. A large part of the difference we see today comes from that shift. Conclusion: modern engines do not offer shorter lifespans because they are weaker. They offer different lifespans because they are designed for a different world. Emission laws became stricter. Consumers demanded lower fuel consumption and more power. Cost pressures increased. Old engines had the advantage of simplicity and mechanical tolerance. Modern engines have the advantage of efficiency and performance. The trade-off is clear. Old engines were tougher. Modern engines are smarter. But modern engines require respect, proper maintenance, and responsible driving, and that is exactly where the difference lies.
Understand your car. Follow for more.